Hello, and welcome to our presentation on prioritized indoor exploration with a dynamic deadline. Most robotic exploration techniques aim to explore the complete indoor environment. They do not consider deadlines. Such deadlines can be imposed by time-critical hazardous environments such as radioactive environments or environments with a fire. They can also be imposed by the limited battery life of robots such as unmanned aerial vehicles. These imposed deadlines cut short the exploration time. The robot is expected to return to the starting location, also referred to the home location. As the robot has a limited amount of time to explore, the exploration should provide useful information. We have two goals for our exploration technique. The first is to perform a prioritized exploration of the environment. The second goal is to identify the layout of the environment. An exploration technique that identifies the layout of the building, such as corridors and how they connect to different rooms, is more useful than a technique that explores only a few rooms in the available time. Here we introduce our three-step method for our prioritized exploration. The first is to create an exploration graph, followed by vertex prioritization, and finally execution of the prioritized exploration algorithm. Here we discuss the steps to create the exploration graph. These steps go from scanning the environment to creating the exploration graph with labeled vertices. We assume that our robot is equipped with a LiDAR scanner to scan the environment. The figure on the left shows a Turtlebot 3 robot equipped with a 360-degree LiDAR scanner. Our algorithm and simulation results are based on this robot with such a LiDAR scanner. A SLAM algorithm is used to create the occupancy map from the robot odometry and LiDAR data. The occupancy map is converted to a skeleton image from which a skeleton graph is created. Here the vertices are marked as gray and white circles. The edges are black dashed lines connecting them. In this skeleton graph, the vertices represent frontier points or intersections of possible paths. The gray vertices denote vertices that have been visited by the robot. The white vertices denote vertices that have been discovered but not yet visited. It is expected that by visiting a discovered vertex, the robot can sense more of the unexplored environment. Edges are collision-free paths between vertices. The cost of each edge is the estimated time to traverse the path. This skeleton graph serves as the exploration graph for our exploration algorithm. As the robot explores the unknown environment, this exploration graph is updated to span a larger explored map. Finally, depending on the geometry of the region in which each vertex is located, the vertices are labeled. The labels represent semantic information such as the building structure associated with the region. As shown earlier, vertices represent the semantic information of the region they are in. We calculate this information based on the shape and size of the available floor region. We assign labels using rule-based classification. For example, a narrow passageway can be labeled a corridor and a room with close-by walls can be labeled a small room. Here we show the details of the rule-based classification. We extract a 3-meter x 3-meter window of the occupancy map. We identify the location and orientation of the obstacles and classify the vertex based on the number of obstacles, distances between them, and their relative orientations. There are 3 examples on the right, each of them centered on a vertex indicated by the black dot. The obstacles are walls, marked by the dark blue lines. The first example shows 2 obstacles parallel to one another with a sufficiently small gap. This is classified as a corridor. If there is just one obstacle, it is considered as a large room. Finally, if there are several obstacles close to one another, it is classified as a small room. Now we come to the second step of the three-step method, vertex prioritization. Here we introduce two exploration strategies, the priority-based exploration strategy and the cost-based exploration strategy. In the priority-based exploration strategy, different building structures such as corridors, large rooms, and small rooms have different priorities. The next vertex selected is the one with the highest priority, and the ties are broken by selecting the vertex with a lower cost. On the other hand, the cost-based exploration strategy assigns the same priority to all structures. It selects the next vertex to be the one with the lowest cost. For ease of explanation, we introduce two agents, Alice and Bob, to represent the strategies. Alice uses the priority-based exploration strategy and Bob uses the cost-based exploration strategy. We come to the third and final part of the three-stage method, the prioritized exploration algorithm. This algorithm has two parts, exploration without a deadline and exploration with a deadline. The first part, exploration without a deadline, begins when the robot starts exploring the unknown environment and continues as long as the deadline is not imposed on the robot. The second part, exploration with a deadline, applies after a deadline is imposed on the robot. Note that the time elapsed when the deadline is imposed on the robot is referred to as TA. The deadline imposed is referred to as TR. The value of TR is updated as time passes to keep track of the time remaining by which the robot has to return to the home vertex. The time elapsed at the end of exploration by which the robot should return to the home location is the total exploration time. It is the sum of TA and TR. When the robot is exploring without a deadline, it selects the next vertex to visit by greedily selecting the vertex with the highest priority. When there is a tie, it selects the highest priority vertex with the lowest cost. To explain the second part of the prioritized exploration algorithm, the exploration with a deadline, we will illustrate with a simple example. The time remaining for the robot to explore the environment after the deadline is imposed is TR. If this time TR is longer than the time for the robot to travel from the current vertex to the home vertex, the robot may be able to visit other vertices before returning to the home vertex. Here the robot calculates the path cost to visit any of the unvisited vertices and the cost to visit the home vertex afterwards. If the sum of the cost of visiting the vertex and the cost to return home is smaller than the time remaining, then the robot visits the node with the highest priority. The robot breaks ties among the highest priority vertices by visiting the vertex with the lower cost. If the time remaining is insufficient for the robot to return to the home vertex, it chooses to explore the environment. It chooses the vertex with the highest priority as long as the vertex can be visited within the deadline. The prioritized exploration algorithm was implemented in IROS for a TurtleBot 3 robot. We have tested the algorithm on 3 simulated environments made in Gazebo. Each of these environments has a different type of corridor. The first one is a straight corridor. The middle one is a looped corridor where the corridor loops around a large room. On the right is the branched corridor where the corridor branches into two parts. Here we show the explored occupancy map and the exploration graph superimposed on it. The yellow lines are edges and black squares are vertices. Here we compare the priority-based exploration by Alice, shown in the top row, to the cost-based exploration by Bob, shown in the bottom row. Each image shows the occupancy map and the exploration graph at a different time step of the exploration. The leftmost images are at the start of the exploration. We see the explored graphs are similar as the robot has not yet moved around to explore the environment. The images in the middle column show the exploration at 500 seconds of exploration without a deadline. At that point, a deadline of 500 seconds is imposed. We observe that the priority-based exploration algorithm has already explored more of the unknown environment as it was able to observe parts of the unknown rooms adjacent to the corridor as it explored the corridor. By the end of the exploration, at the 1000-second mark, we notice that Alice has explored 56% of the environment, while Bob has explored 37% of the environment. This shows that the proposed priority-based exploration has a better result compared to the cost-based exploration. This table shows the performance of Alice and Bob in three different environments. The numbers are averaged over 3 simulations. You can pause the video to see the results up close. I'll focus on a few results. The first set of highlighted results is for the straight corridor environment, for a moderate exploration time of 1000 seconds, with a deadline of 500 seconds imposed after 500 seconds of initial exploration. We observe that Alice explores 100% of the corridor, similar to Bob. However, Alice, on average, has explored more of the large room at the end of the corridor than Bob. Both the agents have explored a similar extent of the small room. Alice has an overall better performance, exploring on average 63% of the environment, while Bob has explored 54%. The second set of highlighted results is for the looped corridor environment, which has a long exploration time of 1500 seconds, with a deadline of 1000 seconds imposed after 500 seconds of initial exploration. Here, Alice and Bob have very similar performances. This happens when the available total exploration time is sufficient to explore almost the entire environment. The third set of results is based on the branched corridor environment, with a short exploration time of 500 seconds, where the deadline is imposed at the start of exploration. We observe that Alice explores 50% of the corridor and a higher percentage of the total environment. Taken together, these show that Alice has an overall better or equal performance when compared to Bob. To conclude, we have proposed a prioritized exploration algorithm for indoor environments. It works with a dynamic deadline imposed during the exploration. The robot returns to home within the deadline after the exploration. This makes the technique suitable for time-sensitive, hazardous environments. To extend the work further, we will change the rule-based vertex classification of occupancy map windows to neural network-based classification. This may enable better performance in assigning labels in non-rectilinear environments. Additionally, we can use different sensors such as a camera to recognize building structure. Lastly, we can use multiple robots in parallel to compute the exploration faster. I'd like to thank the entire robotics lab at UNC Charlotte and acknowledge support from NSF for this research. Thank you for watching.